All right, we'll just wait another minute or something. On, you can we'll just keep just this schedule. All right. Okay, I think we'll carry on. I'm starting 1 minute early. I don't want to get any earlier than that. Okay. So this next presentation is going to be by Pawan Negi, and it's some flexural gravity wave interaction with a circular polynya in the context of wave blocking. Okay, take it away, Pawan.
Okay, thank you. Good morning, everyone. Today, I, Pawan Negi, research scholar in the Department of Ocean Engineering and Naval Architecture at IIT Kharagpur, will be presenting on flexural gravity wave interaction with the circular polynya in the context of wave blocking. This work I'm currently doing with my supervisor, Professor Pawan Sahu, and with Professor Mike Millen. So the outlines of the presentation are: first, I'll talk about the objective and the motivation for the present study, then some relevant literature review. After that, I will go into the mathematical formulation, which will constitute the basic physical assumption for the mathematical modeling, the governing equation, and then we will analyze the dispersion relation in the context of wave blocking that Professor Sahu has already done. Now, then I'll discuss about some results. Basically, I will be focusing more on the polynya deflection and the ice sheet deflection. Then I'll conclude my talk and then some references. Actually, last work was done on what Professor Sahu has done was done on the Cartesian coordinate, but I will be doing it in the polar coordinate system. So my objectives are to study the interaction of flexural gravity waves with the circular polynya in the context of wave blocking. So the said problem is studied in three-dimensional fluid domain in the polar coordinate system under the linearized water wave theory and small amplitude structural response. Also, the dispersion relation will be analyzed for multiple propagating wave modes in the context of wave blocking. Then the solution for the single wave mode, propagating wave mode in the ice sheet will be expanded using the eigenfunction expansion method. And then it will be generalized to account for multiple propagating wave mode. Then we have some results on ice sheet deflection and polynya deflection and the resonating factor also. And so coming to the motivation, we knew that the various geophysical processes, upwelling and wind stresses and geothermal effects could have a notable impact on the ice sheet in the polar region, because of which such openings are formed in the continuous ice sheet, which we refer to as the polynya. They are the open water regions. These polynyas can be classified into two categories, mainly the coastal polynya and the open ocean polynya. These open ocean polynya occurs in the interior of the ice packs, which are formed due to upwelling of the warmer water. One of the major importance of this polynya is that they help us to transfer heat and moisture across the ocean and the atmosphere. So they kind of a bit control the polar climatic ecosystem. Also, these polynyas are important for the marine habitat so that they get enough nutrients and open water space. Now, coming to the literature review, although many work has been done on the floating ice sheet and the wave scattering by such ice sheet, but I'll cite which are quite relevant to my work. Here, the Bennett and Williams, starting in 2010, analyzed the wave scattering by ice flows and the polynya of arbitrary shapes using the Green's function technique. Then Lee et al. In 2017, 18, and 20 studied the interaction of floating body in the polynya using the white space approximation. The first study in 2017 was done in the Cartesian coordinate system, and the followed study in 2018 and 2020 was done in polar coordinate system, but using the Green's function technique. Then Das et al. In 2018 studied the dynamics of the flexural gravity wave blocking, and he pointed the existence of multiple propagating wave mode between the blocking frequency. Then In the context of series of polynya, Sunil et al. In 2023 studied the scattering of fractal gravity wave within the framework of wave blocking. There they demonstrated the occurrence of Bragg scattering due to multiple polynyas. Now coming to basic assumption and the schematic diagram, here we assume that the complete fluid domain is inviscid incompressible and the flow is irrotational. Also the motion being simple harmonic in time with frequency omega. Also we have a continuous ice sheet, but we have a gap in between, which is a circular polynya. Only here a two-dimensional picture is shown. Basically the radius of the polynya is A, and then the ice sheet, as we have said that the small structure amplitude response is assumed. So we model the floating elastic plate using the Euler-Bernoulli beam equation with the inclusion of lateral compressive force in the polar coordinate system. Further, the velocity potential and the plate deflection exist and are of the form. They can be split into the spatial components and also the time part. Now coming to the mathematical formulation, the spatial velocity potential phi j r theta y and the plate deflection eta, which is a function of only r and theta, and in each region will satisfy this Laplace equation in the polar coordinate system. Here, basically in all this region 1 and 2. And the bottom boundary condition, because we have considered the bottom bed to be rigid and impermeable, we have the normal component of velocity is 0. Then we have the linearized kinematic boundary condition on y equals to 0. Now, the boundary condition inside the polynya can be written like this form, and whereas in the ice-covered ocean, it can be derived in this form, where my d is equals to ei by rho g, known as the fractional rigidity. Q is a term inclusion of compressive force, that is n by rho g, and my gamma, this is my gamma term, basically the inertia term. I have not ignored the inertia term in my computations. Also, here my rho p is the structural, basically ice density, rho is the fluid density, and g is the acceleration due to gravity. Further, along the interface of the polynya and the ice covered region, basically at the edges of the ice sheet, we have the continuity of pressure and velocity, which gives us phi 1 equals to phi 2 and del r phi 1 equals to del r phi 2. At r equals to a, basically the radius of the polynya for all depth and for all theta. Now coming to the free edge and far field condition, because we have assumed that the ice edge is free to move, which leads to the vanishing of the bending moment and shear force at the ice edge, and we write this equation in the polar coordinate system in this form, and the far field condition are given by this. Here, my phi naught is the incident velocity potential, which is given like this, where h naught is the amplitude of the incident wave, p naught is the component of the incident wave traveling within the ice sheet, and then we have this epsilon m jm p naught r cos m theta. Basically, this is the Jacobi-Iyengar identity used to conversion from Cartesian to polar coordinate, and jm are my Bessel function of the mth order, and the epsilon m are given by 1 and 2 to the power of im for m greater than equals to 1. Now, as Professor Sahu has discussed, when we come to the plane wave characteristics in the ice sheet, we arrive the dispersion relation in the ice covered region of this form, and the phase and group velocities are given by this. It can be easily checked that the phase velocity will vanish. This phase velocity C2 will vanish for 2 root d, and the wave number will be 1 by d to the power of 1 by 4. Here QC is refers to as the buckling limit of the compressive force, and PC basically the critical wave number, because at this buckling limit of the compressive force, there may a fracture or a crack may be initiating in the ice sheet. Further, the group velocity will vanish for Q equals to QCG and the wave number PCG. That has to be numerically found out from the plotting of the dispersion curve. Here, QCG is referred to as the threshold of blocking limit, and PCG is the point of inflection or saddle point, which I'll show in the next slide. Now, here we have done the plotting of the dispersion curve for time period versus wave number. Professor Sahu has done with wave number versus frequency. So here we can see when Q is less than basically the pink and the blue or the red curve, we have the existence of single propagating wave mode for each time period T. But when we slightly increase the compressive force, we have the occurrence of multiple propagating wave mode for each time period T. Like for T equals to 60 seconds, we have 3 multiple propagating wave mode. Now, all of these 3 routes either will collide at the blocking point, which is referred to as the primary blocking point, or at the secondary blocking point. But one of the interesting feature is here that all these 3 routes will collide at one point, which we can see on the green color curve, which we refers to as QCG and is called the threshold of the blocking limit. Here, the value of the threshold of the blocking limit is 1.6725. In my computation also, I will stick to Q equals to 1.97, and the time period will be taken around 60 seconds, considering these multiple wave modes. Now here we have plotted the group velocity and the phase velocity curve. So we can see that at the blocking point, my group velocity is 0. That is, my group velocity vanishes. However, my phase velocity does not vanishes. And we can see between the 2 blocking points, my group velocity is negative. So wave numbers corresponding to this negative group velocity will not be taken up as a incident wave modes. And also at the settle point, we can see that the group velocity attains a 0 minimum. Now, coming to the method of solution, we have used the Fourier Bessel series to write the special component of the velocity potential, and thus we inside the polynya or the ice in the ice covered region, basically phi1 is my ice covered region, and the potential is expanded in this form, whereas inside the polynya the potential is expanded in this form. Now here we can see that this part constitutes of the incident wave. This part is my propagating wave mode, which will be the predominant scattered wave mode, and it's written with the Hankel function of the first kind. And then my P Roman 1 and P Roman 2 are the complex conjugate wave numbers of the form A plus minus IV. But here we can see for the boundedness, we have taken Hankel function of the first kind and the second kind for A minus IV, so that my complete solution remains bounded. Now in the open water region or inside the polynya, I have my expansion, which is the Bessel mode, and then we have the Evensen mode contribution. Also here my M is my the angular modes. Now we define the vertical eigenfunction in the ice covered and the open water regions, which are of this following form. So we will use the eigenfunctions orthogonal mode coupling relation corresponding to the open water region, which are psi mn, and they are basically the combination of y component and theta component, and they satisfy this orthogonal relation. And where my c kn is equals to f prime, which is a derivative of the dispersion relation in the open water region, and then capital K is equals to omega square by g. Also, using this, we have a system of 2n plus 4 unknowns, and thus we derive the system of 2n plus 4 linear equation for the computation of these unknown constants, am0, am Roman 1, Roman 2, and then similarly bm0s. So this is the system of equation that we have derived for 2n plus 4 equations for deriving the unknown coefficients. Okay. Now coming to the physical parameter for numerical computations, we can see these are the following parameters we have fixed for the numerical computation. Here the time period are considered only inside the blocking region. Here the ice deflection, the water elevation inside the polynya, and the flow around the polynya are demonstrated using the contour maps for various parameters. Now coming to the results and discussion. Okay, so we have actually we have this infinite series. So we have considered n equals to 15. That is the number of events and modes are considered 15, and the number of Bessel modes are considered 80. So that we have a proper formulation of the incident wave. Sorry. Now here we have plotted the ice sheet deflection for different compressive forces. But we have restricted here Q is less than QCG, and we can see that the plane incident wave propagates from left to right and then encounters a polynya. It kind of scattered around the polynya as the compressive force increases. Also, we can see that the plate deflection increases. The kind of plate deflection increases when we increase the compressive force from 0.8 to greater than 1 and then greater than 1.5. Also, when we increase the compression, the number of crust and troughs in the scattered wave field are more, and basically in the shadow region, basically the region behind the polynya, the deflection becomes very less. Now here, what we have done, we have taken the cross-sectional plane z equals to 0 and try to see the deflection in 2-dimension. So this blue color curve represents the deflection inside the polynya, and the red curve is the ice sheet on both the side. So we see that the pattern is quite regular because we have just one propagating wave mode. The other two are basically the damped wave modes, P Roman 1 and P Roman 2. Also, that deflection on the transmitted side is more on when the compressive force is 0, but when the compressive force is introduced, basically the reflected side deflection is higher. And here, the radius of the polynya was considered to be 500 meters. Now, these are the contour flows for the same that gives the complete flow distribution inside the polynya and outside the polynya. So that we can also observe that when the compressive force is introduced, the waves are more scattered when they encounter this polynya, the waves becomes more scattered. The waves kind of scatter more for higher compressive forces. Okay, now coming to the picture when we have the blocking. So here I have fixed Q equals to 1.98 root D and the frequency is 0.3. We can see that from the previous results, and here the results are plotted for different radius of the polynya, 300, 500 and 700 meters. And we can explicitly see that in the close proximity of the polynya, the plate deflection is irregular and there's a large up and down in the ice deflection. Also, however, the deflection, the amplitude of the deflection remains the same for all the three cases. But this irregular behavior is because of the interaction of three propagating wave modes in the ice sheet. Now, similar analysis has been done for considering the blocking compressive force Q equals to 1.9 root D, and for different polynyas, radius polynyas. So here we can see obviously the ice sheet deflection are irregular, but the polynya deflection are somehow irregular because only the wave number K0 is propagating over there. And also the number of crust and trough increases as the radius of the polynya increases, which is quite obvious. So here we show the flow distribution with QA higher compressive force. We can see that the flow distribution looks like very congested when we have the multiple propagating wave mode, and the amplitude of the deflection on the reflected side is much more than in the transmitted side for such a case. Now the diffracted far field amplitudes are plotted here. In the first case, we have restricted ourselves for Q less than QCG, and we have three different values of Q, and we can see as my Q increases, my diffracted far field amplitude also increases. But however, and the maximum amplitude is observed at theta equals to 0, which is obvious because which is also obvious because theta equals to 0 corresponds to the direction of the incident wave. However, when we have the symmetry, like when it goes to minus pi or pi, this diffracted far field amplitude converges to 0 irrespective of the values of the compressive force, because theta equals to 0 corresponds to the shadow region behind the polynya, and pi and minus pi and pi represents the direction of the incident wave. Now coming to the case when we have the higher compressive force and we have the blocking effect, basically this diffracted far field amplitude is a contribution of three terms. So we can see as the radius increases that this amplitude increases at theta equals to 0, and moreover the diffraction is all over the theta irrespective of the previous case, we can see at theta equals to minus pi and plus pi also, this does not converges to 0. Now coming to the conclusion. The ice sheet deflection increases with an increase in the value of the compressive force. And obviously the ice sheet deflection is regular for Q less than QCG and irregular for Q greater than QCG because of the interaction of 3 distinct propagating wave modes. Also, the irregularity in the ice deflection increases as the radius of the polynya increases, and the DFFA increases with an increase in the value of the compressive force as well as the size of the polynya. Here are some of the references I've used for the present study. At last, I'd like to thank you all for your kind attention. And
All right, thank you, Pawan, so much, and another great talk, and perfectly keeping to time as well. All right, so someone's got a question to ask. So
yeah, Pawan, can you go to your literature review page? Borman et al., not Sunil et al.
okay. Oh, I'm extremely sorry.
And Pawan also, where you present your assumption and modeling, you put phi xy, that will be r theta.
So actually, phi r theta, yeah.
Okay, just wait in this slide. No, that 2-dimensional figure slide.
Yeah,
Section.
that,
Go down.
Yeah.
Here r theta is Pawan, go down to the result in deflection before blocking. 2-dimensional figure, deflection.
Yeah, I'm going.
Go down.
So some you've clearly been paying attention to this talk. We don't need to have some typos spotted. What's your question?
Yeah, here probably in figure B, what's the deflection on right is not uniform. It looks like some parabolic pattern. Why is that so?
It's not kind of a parabolic pattern. If I have taken the more range, it will look like quite regular, and moreover, it shows the shadow region behind the polynya. So maybe the scattered wave.
Look, it's not uniform. The amplitude in middle, like near 1000, it is higher and then it is going down. This is what polynya effect.
Yeah, basically, when we look at the circular geometry, the energy got distributed in all the directions. But here I am plotting just the z equals to 0 plane for the better clear view.
Okay.
But for that you have to see this picture, because if you see on this, like what should I say, on on these planes, these pictures, we see the scattered wave quite easily, and then in the shadow region there is not much deflection. But here we have taken just the z equals to 0 plane, like this line only we have considered for the better clarity of the deflection, that it is regular because of the single wave mode.
In these figures, what about that water elevation that you are not presenting, right?
Yeah. Actually, that I have not presented because they are quite regular and it was not of much of interest. So only I have plotted the 2-dimensional picture here. I would have included those also. Yeah, sorry for that.
Pawan, go back to that figure,
Okay.
the previous one. Sorry, so I'm not going to. You can ask your question, but just a comment that in the far field, eventually it would return to the. You go far enough back, eventually you just return to the plane wave.
Yeah. Basically more, I have to take more distances, large distances at x and z. Basically, I've considered only because the radius here I think is 500 meters. So maybe if I go to 1500 or 2000 meters, so then it will return to a plane wave.
So Sam, what was your question you wanted to ask?
I have a small question. When you consider an ice compression, do you take into account limit of force compression force due to the possible buckling of the ice sheet?
Yeah. That buckling limit Basically, I have not plotted here in the Professor Sahu slide. You might have seen that the Q equals to 2 to D. I have not plotted here, but in the Professor Sahu slide, he has shown that the group velocity becomes discontinuous, and there also we have a sharp point in the dispersion curve at Q equals to 2 root D. Basically, that is the point where the fracture or the crack may initiate in the structure, and if we go beyond that limit, maybe the structure will buckle and a devastating thing can happen to such a structure or the ice sheet. So we have, for my presentation, I have not considered that compressive force. Basically, the value is 2 root D, that I can tell you, and I have not plotted it here also.
Many sense.
If the compression becomes greater than that, then the plate has more energy bent than straight. And so, you know, the plate, if a bent plate has less energy than a straight plate, and then of course it just keeps bending and breaks. That's the idea of that.
Okay.
If you had an infinitely long beam, then it's always got less energy bent, but because of the gravity restoring force, it takes a certain amount of compression to have it, given that it's infinitely long.
Okay.
I've got a question that have you tried to validate this by looking at some results for the energy in the far field or some energy conservation results?
No, I have.
And if you have done, are they different because of this multiple propagating modes?
So I actually, when we plot the diffracted pattern, one thing I have noticed that it does not go to zero at the direction of the incident wave. That is one point, and basically it's a combination of three modes. But if I plot them separately, then it will be more clear that I have not done. And coming back to the energy relation in the circular geometry, as suggested by you, the optical theorem I have tried, but till now I'm trying it. I have not got it till now, the energy relation using the optical theorem.
Yeah, because it'd be interesting to try and analyze that. That's perhaps one of the things we should look at. Yeah, because I think it'll be very interesting what happens when you have this multiple propagating modes. Never. All right. Is there any other questions? All right, Pawan, thank you very much.